In this tutorial, we're going to be looking at the transmission and weight graphs, and how we can use these graphs to determine which images to reject. This option is disabled until we've run NSG. I've already done that, so we can display the graphs straight away. We can show a sky transmission graph and also an image weight graph. And we can modify the minimum criteria to reject more or less images. But why do we need to reject any images at all? If an image has a low weight, providing that weight is accurately calculated, then in theory it should still improve the signal-to-noise ratio of our final stacked image. The problems really occur if our low-weight images have other problems as well, and I shall explain that as I go through the features. So I'd like to start first with the transmission graph. Now in this graph, how transparent the atmosphere is completely independent of the amount of twilight or moonlight or artificial light pollution. All that matters is how transparent the sky is. So in this observing session, despite the fact that I started before twilight had fully finished, we can see that the sky transparency was very constant until towards the end of the night, when light clouds formed, and that started to absorb some of our astronomical signal, so our sky transmission ended up reducing. And I particularly want to penalise images that have clouds, because clouds can end up affecting the image unevenly. Now this might mean, for example, whereas normally the brightness scale factor is a single constant for the whole of each image, if it's been unevenly affected by cloud, you might have some parts of the image which are particularly bright, and other parts of the image where the brightness scale factor ought to be considerably lower. And this is something that's very difficult to accurately correct. As well as that, light clouds will end up reflecting light pollution, and that can produce some very complex gradients, which may be difficult to remove. So we can spot and reject the images which were affected by cloud. For example, if cloud had drifted through our field of view in the middle of our observing session, we would see a sudden dip in the transmission graph. And we can see that that's exactly what's happened on our last point in the imaging session as the light cloud built. So all we need to do to reject it is to increase our minimum transmission a bit, and if a point's been rejected due to the sky transmission, is given a blue cross. Our default value for minimum transmission is 0.75, and because of the signal-to-noise ratio squared relationship with weight, 0.75 corresponds to an image weight of approximately 0.5. So we can now move on to the weight graph, and we can see that this point at the bottom right has been rejected via our transmission graph. We now need to look at the other images that, although the sky transmission was good, they still ended up with a low weight. And that happens when our sky illumination was higher. So that can be due to twilight, moonlight, artificial light pollution, or even sky glow. Now, the moonlight and twilight, they tend to produce fairly simple gradients. They might be strong gradients, but they tend to be fairly straightforward to remove. So I would actually want to keep these images here. I think they'll all likely improve our final result. And NSG will remove the gradients that they had very easily and effectively. But if the sky brightness ends up becoming too high, we end up with other problems. So for example, if our flat calibration isn't perfect, the brighter the sky background, the more those errors end up affecting us. And you've probably seen this already. If you take a hydrogen alpha narrowband image, you find that flat errors tend not to be a problem. But if you take a galaxy with no filters, then flat errors tend to be seen in all their glory. Dust donuts and vignetting become very apparent. So we might want to reject images with a very low weight to reduce the impact of any flat calibration errors. And there's also another reason we might want to reject very low weight images. And that's that once we've normalized a low weight image, the higher noise, the lower signal to noise ratio, causes the amount of deviation between the pixel values to be much higher. And this causes a problem within image integration while it's trying to do its data rejection. It's looking for outliers in order to spot the satellite trails, the hot pixels we might have missed, and things like cosmic ray strikes. And it's harder to find outliers if our data has too much spread in it. So I feel that you're unlikely to want to include image weights that have less than the default value of 0.25. And depending on your data, you might want to increase that further. But we've already taken out the images that were particularly troublesome already from the sky transmission graph. So very often there's nothing to do when we get to this graph. We can see that this graph has a green cross on it, and that represents the NSG reference image. And you can left-click on that to display the file name in the title bar. And in fact, we can left-click on any point to show its file name. I'd also like to bring your attention to the data displayed in the bottom row down here. We can see that since we've rejected only one image, we're using 19 out of the possible 20 images. And that gives us a total exposure time of 1 hour and 35 minutes out of the possible 1 hour 40. I also show you the weighted exposure time. And here we can see that by rejecting one image, one 5-minute image, we've only reduced our weighted exposure by 2 minutes. And that's because the lower weight of the image we've rejected means it has less effect on the weighted total. Now, the other thing I need to mention is for those that sometimes have mixed exposure times in their data. Perhaps you're combining data from previous years. This graph ends up compensating the weight for exposure time. Now, that's not a completely intuitive thing to do, so I think I need to explain why I do that. And I think a thought experiment will illustrate the point. Suppose we have 3 images, 2 5-minute exposures and 1 10-minute exposure. And suppose that these exposures were taken in perfect conditions. The 2 5-minute exposures will clearly have half the weight of the 10-minute exposure. But there was nothing wrong with those 5-minute exposures at all. There is no reason why we should reject them. They don't fit any of the criteria that we've mentioned. So by scaling them by exposure time, we're then displaying them on an even playing field, and we end up only rejecting those images that had problems that end up requiring them to be good candidates for rejection. Now the next thing I want to show you is for those that use drizzle integration. If you're using drizzle integration, we need to tick the drizzle data box, and what that does is just NSG will find the drizzle data files, and when you exit NSG and it invokes image integration, it will add the drizzle data to image integration for your convenience. And I think I should remind you of what the drizzle integration process actually is. So you'd first run NSG. When you exit NSG, image integration will be displayed. It'll populate everything with our target images, our local normalization data files, and our drizzle files. The image integration will then add data rejection data to the drizzle files, and then finally, when image integration has finished its run, you then need to run drizzle integration manually. And here's the tricky bit. Because we ended up rejecting some of the images in image integration, it's vitally important that we don't include those rejected files in our drizzle integration. The two have to match as a one-to-one file correspondence. And that can be a nuisance. It can be a bit of an extra task that's annoying. So I would recommend, if you're using drizzle data, to use this option to move the rejected images and all their data files to an NSG reject subfolder. Then it's straightforward. When you're running drizzle integration, you just need to use all the remaining files that are in your main directory, and it's just straightforward and easy. So I don't have drizzle data for these files. Let's uncheck that, and then make sure that the image integration section is checked, and then we can exit NSG and image integration will be displayed. And we can see that our rejected image has a red cross against it, and that tells us that image integration will ignore that image. It won't include it in the stack. So we can then modify our rejection parameters and run run image integration. I won't do that now, but I wanted to show you something else. Suppose that after we've run image integration, we decide that, well, actually, I'd like to see what the result would look like if I rejected a different set of images. Now that's easy to do. We can go back in to NormalizeScaleGradient, and it remembers all our settings from the previous session. And it remembers the data that it calculated, so we can still display the transmission and weight graphs. And if we wish, we can change the settings. And then when we exit, it will bring up image integration again, and we now have two rejected images instead of one. But suppose we wanted to come back in several months' time and rerun the process. Well, if we've done a little bit of setup work when we first run NSG, that's easy to do as well. So after our initial run, what we need to do is save a process icon by dragging a little blue triangle onto the PixInsight desktop. We can now exit NSG, and we can click on the top left N of the process icon and give it a meaningful name. Then we can save the process icon to disk, and then several months later we can load them back in again, and to run it we can either double click on it or select execute in the global context. And of course our process icon has remembered all the settings within NSG. And providing we haven't moved or modified any of the input files or the data that NSG calculated, then the transmission and weight graphs will still be available. NSG will look at the file modification dates to make sure that this is indeed the case. So we can display our graphs, and let's say we wanted to return the weight, minimum weight, back to its default, like so. And then when we exit again, we can see that image integration is brought back up, and now we only have one rejected image. So it's a nice way of recording what you did. It's a nice way of being able to redisplay the graphs that provide you with a good feedback on what happened during your observing session. So I think it's quite a useful feature. One extra thing I would like to show you finally is the transmission graph can show you one other type of situation. And that's if we're imaging an object that had a low altitude, then as the object rises and sets, the amount of atmosphere we're looking through can vary quite dramatically. And that can change the sky transmission. And we can end up showing that by, instead of sorting the images by observation time, we can instead sort it via the optical depth that's calculated via the stored altitude. And when we do that, on this data set, the image was high in the sky, so we can see that there's no real correlation between increasing optical depth and sky transmission. But if the object had been low in the sky, then we should see that the transmission ends up falling in a fairly uniform rate as the amount of atmosphere that we're looking through increases. Of course, it depends on whether there's clouds as well, which might muddy the graph somewhat with some downward spikes as well. Right, I hope you've found this tutorial useful, and I hope you'll join me for the next one.